is Elizabeth Alpino, but she's not here at the moment. And so I will start chairing the session. If she comes, then she'll take over. So it's my pleasure to introduce Reinaldo Santos-Lima from IAG-USP, and he's going to talk about turbulence, I think. Turbulent transport of astrophysical magnetic fields. Can you share your screen, Reinaldo, please? Okay, the floor is yours.
Yes, now I think everyone is seeing my screen, right? Good afternoon to everyone. Thank you, Rogério, for the introduction. I'd like to thank the organizing committee, Elizabeth Alpino, for this invitation to talk about this work. It's a pleasure for me to be here. And I was telling here before the session started that I'm going to present some results. That's the first time I participate in this conference, Challenge of Neophysics in Space. It was to talk exactly about this work, the early results we got by that time. I think it was 2010. It was February 2010. And well, thanks for the presence of everyone. I would like also to thank my collaborators for this line of research. I'm going to talk a little bit today. Gustavo Guerreiro, who is present here, Elizabeth de Gouveia Dalpino, Alex Lazarian, and more recently, the undergrad student Camila Koshikumo from IAG-USP. So I'm going to talk about the turbulence transport of magnetic fields that take place in several situations in astrophysics. For example, in the galaxy, during the process of the dynamo of the galaxy, also inside in the interior of stars, in the process of the dynamo, inside molecular clouds, in the intracluster medium of the galaxies. So, but the motivation of this research I'm going to present started in the context of star formation, in order to understand the role of magnetic fields. What about the transport of magnetic flux, magnetic fields in the context of star formation? So the star formation, the processes happen in different scales. It starts in parsecs scales in molecular clouds, and it goes down to subparsec scales when you have the contraction of a dense core that can or not proceed to a collapse to form a newborn star, and also in late stages when you have already a protostar formed and you and there is a production of a rotationally sustained or a Keplerian disk around this protostar that can give origin to a planetary system. So in all these stages of the star forming process, you have the presence of magnetic fields and incidentally turbulence and some problems related to understand what's the influence of the magnetic fields in this process. So the first problem I'm going to talk about happens here in the subparsec scales when you proceed from the collapse from a dense core that's supercritical. It means it's going to collapse to form a star because magnetic fields cannot provide support enough to avoid the gravitational collapse. And when it happens, it's our estimations of the electrical resistivity of these environments show that the diffusion due to the ohmic resistivity is not fast enough to prevent that a lot of magnetic flux that was permeating this core would be brought together with this collapsing material. But if this is the case, if this frozen condition is really valid, so we would have what's called the magnetic flux problem, because the T-tower stars would have magnetic field intensities, orders of magnitude higher than what's really observed. So it's necessary some process that allow this magnetic flux to slip from this region or to be redistributed. But this process has to be effective. It has to be the order of 1,000 times more effective than the ohmic resistivity. So usually the unbipolar diffusion is thought to be the solution for this problem, because this environment is cold, so you have a lot of non-ionized neutral material. So this material is not directly connected to the field lines. So the dynamics of the magnetic fields is influenced by this neutral material through their interaction, through their collisions with the ionized material. So the description of the evolution of the magnetic fields in this situation would have a term, a diffusive term, the bipolar diffusion term. But for many decades, this was thought to be the solution for this problem. But its the efficiency of this has been challenged by observations and theory. Its necessary conditions very special, so that it would provide this necessary diffusivity of the field lines to explain observations. So it was proposed by Alex Lazaran and us that maybe turbulence, the turbulent transport of the field lines could solve this problem. This is because the turbulence in this environment would induce magnetic field reconnection that was discussed by the early talk by Grzegorz Kowal. And this reconnection, this entanglement of the field lines produced by turbulence would make several points where you have some components of the magnetic flux opposites, and it would proceed to reconnection and change of the topology of the field lines. So it would allow the large scale magnetic flux to slip from this region. So you would have some effective transport of magnetic flux from the central region, from this potential well to envelope of this core. So using the statistics of the magneto-hydrodynamics turbulence in the situation where this large scale, this ambient magnetic field has real intensities, so it would be dynamically important. So it would produce some statistics of the turbulence that allowed Alex Lazaran to predict what would be the diffusivity of this process. So the diffusivity would be given by the turbulent mixing rate, which is the scale of the eddies of the turbulence multiplied by the velocity of these eddies. So this is the classical mixing rate. But an effect of the dynamics of the forces of the magnetic fields on the dynamics of the turbulence would be some suppression that is given by this ratio between the turbulent velocity and the alpha velocity, which is proportional to the intensity of the field lines, to the power of 3. So this number is smaller than 1. It's in this environment usually. So it would produce somewhat strong suppression. So this photo of coffee mixing with milk represents this process of turbulent mixing. So we can see here some eddies in this 2D view. The difference with our situation inside molecular cloud is that instead of mixing material, turbulence is mixing field lines, large scale field lines. And here you are mixing material which is not interfering with the dynamics of the turbulence. But when you have magnetic fields, the magnetic fields themselves, they interfere with the statistics of the turbulence. And we showed about 10 years ago that this process that we term the reconnection diffusion indeed could solve this magnetic flux problem. And we showed through numerical simulations where we studied a scenario where we have a core contracting in the presence of the turbulence, and we showed that in this situation, the ratio between the magnetic flux and mass crossing this core, it reduces with time, effects of the turbulent transport of magnetic fields. Indeed, in this study, it was also shown that this transport could turn these cores that are sustained by the magnetic forces into supercritical. If you remove enough magnetic flux, this core can lose the support, the magnetic support, and could proceed to collapse. Even more, this process can explain better the mass to flux ratio between the cloud core and the envelope, the external region, something that the bipolar diffusion cannot explain well. And it was exactly these results I presented in this series of conference about 10 years ago when Opher invited me. And it's very interesting to present here 10 years late some advancements of this study we started in that time. And about 1 year ago, when I presented these results, someone asked me, but why do you need turbulence? Because you have other mechanisms that could redistribute magnetic fields, like a bipolar diffusion, maybe some enhanced electroresistivity somehow could be enhanced by increase of temperature. But this question is not very good because turbulence is there, and whatever is the mechanism you are taking into account to study the process, you should take into account the turbulence, because we can measure turbulence is in the interstellar medium in several scales, from astronomical units to dozens of parsec scales. And a natural source of the injection of mechanical energy here, and probably the most important are the explosions of the supernovas. So the expansion of the supernovas, but also the passage of the spiral arms, and we have other local sources like outflows. And as you have some source of mechanical energy, turbulence will develop, because the Reynolds number of this the environments in the interstellar medium is usually very high. So the Reynolds number, which is measures the importance of the advection with respect to the viscous forces, when it's much larger than 1. So any disturbance in the system will lead the system to develop turbulence. In other words, it's very difficult not to have turbulence when this Reynolds number is too high. And it happens in most of the astrophysical environments. Usually it's very high. In fact, in the last years, we could see the turbulence present inside the molecular clouds, from some parsec scales down to hundreds of astronomical units scales, as we can see from this region, these star-forming regions in serpents from these polarization vectors. So this data is consistent with turbulence present in this environment. So as this reconnection diffusion, we showed that it could explain some phase of the star forming process. We applied this to another phase, to the formation of the proto-stellar disks. It's not very clear how do these Keplerian disks forms in this environment when you take into account the presence of magnetic fields with realistic levels. This is because the presence of magnetic fields they avoid the formation of the disk, because these field lines, when they rotate differentially with this disk that's about to form, so these field lines exert torques in this rotating material, and on the other side, these forces on the field lines will produce distortions in the field lines that are transporting the angular momentum, extracting angular momentum from the disk. So it makes so this disk loses the rotational supports, and the material directly falls to the protostar. But in this situation, the disk would not form. But we know that these protoplanetary disks, they exist. So it's a challenge to explain how, which mechanism allow them to form. So we thought maybe turbulence could remove some of the excess of magnetic flux crossing this disk, and avoid this process, or at least alleviating a little bit this extraction of angular momentum. And we studied numerically a scenario where we had the scenario where we had the formation of this protostellar disk in the presence of turbulence. What is shown here in this image is face-on view and side-on view of this disk with the turbulence in the environments. And with some level of the turbulence, we observed that a disk really formed, contrary to the case where we did not have turbulence. So in this case, we can study the profile of the rotational velocity, and we see clearly that's not Keplerian here, but here it is. And the radius of the disk formed is consistent with the radius of the observed ones, around 100 astronomical units. So in principle, reconnection diffusion could also solve this problem of allowing the formation of these Keplerian disks. So can resolve this problem called magnetic braking catastrophe, where you would not have the formation of this disk. Okay, but different mechanisms are competing to diffuse magnetic fields during this process of formation of the disk. The bipolar diffusion, some enhanced ohmic resistivity due to the increase of the temperature in the internal parts of the disk, and also the reconnection diffusion because turbulence is present there. So which one is the most important? Which is the one that allows the formation of the disk? So we still do not know some observational signature that each of them imprints on these disks. So from now we cannot tell from the observations, but what we can do is to compare the efficiency of each of them separately. But the problem with the reconnection, with the transport by the turbulence, the reconnection diffusion, was that we still did not have a quantitative test of the theory or a validation of the predictions of the theory by that time when we showed these results of the formation of the disk. So what I'm going to show from now are some results that we published this year, where we successfully tested quantitatively this transport. We tested the dependence of the parameters of the turbulence, and this validation of the theory now allows us to interpret better the numerical studies where you want to represent the effects of the turbulence. So it has also implications not only for star formation, but also for the process of dynamo in several objects and scales, because when the turbulent dynamo is working, the transport of magnetic fields, the diffusion of magnetic fields is an important component of this turbulent dynamo. And it allows, for example, the development of this work which is in progress, where we are trying to understand what's the minimum requirements of the turbulence, what's the minimum, let's say, parameters of the turbulence, velocity of the turbulence that would allow the formation of a Keplerian disk. So and also at the same time to characterize what's the features of the disk formed in different levels of the turbulence. So for example here, in this work by Camila Oshikumo in preparation, we show here the profile of the rotational velocity of the disk formed in the presence of the turbulence, and this is the Keplerian curve. So the curves of different colors show scenarios where the different parameters of the turbulence are used. When this line separates from the Keplerian, it means that the disk finishes at this point where this line separates. So we are trying to characterize for different levels. Yeah, we already saw what's the minimum requirements of the turbulence to have a minimum disk formed. So let's come back to the reconnection diffusion theory and predictions. So the idea here is to test the prediction to understand first if it makes sense, this theoretical understanding of the transport of magnetic field based on reconnection. So with all these hypotheses and also the assuming some statistics for the turbulence happening there in the situation of strong magnetic fields. So Alex gave this prediction, Alex Lazarian, for the diffusivity. So we studied if this verify or not. Yeah. And we did that using
sorry,
magneto. Yeah.
You have 5 minutes. Sorry.
Okay. We used magneto hydrodynamic simulations, 3 dimensions of forced turbulence. We access the diffusivity, the amount of the diffusivity or the rate of diffusion of the magnetic fields using this test field method. So I'm going to show here what were our first results some years ago. So this plot shows as a function of this ratio, the turbulent velocity and the alpha velocity, the diffusivity. So the theoretical prediction was to follow this power here, this curve much more steep than what's shown here. But what we obtained from the simulation is totally different from the theory. And the same was obtained by other groups by that time. Different groups, so they came to the conclusion that the numerical evidence is not arguing with this picture of reconnection diffusion. But we insisted, we thought that could be some artifacts in our simulations and other group simulations in the way, in the setup, in the way that people use to study this problem. So we finally investigated what would be these deviations, and we arrived to the conclusion there are 3 sources of deviations here. One is the compressibility of the turbulence that changes the statistics of the turbulence. The theory is built on hypothesis of purely alpha-venic turbulence, which means in the limits of incompressible turbulence. And other artifacts we found studying for several years this problem. We found some artifacts were affecting our results and other groups too, due to the numerical setup. One of them is the size of the computational domain, and also the model we employ to represent, to inject turbulence in the system. So I will highlight each of these effects quickly, as I'm showing here, the different ways in which you put turbulence in this system in order to make your measurements, in order to make your simulation measurements. So it shows here in the left-hand side the power spectrum, the bidimensional power spectrum. So here in this axis, the wave number perpendicular to the mean field, mean magnetic field in that system, and here the wave number parallel to the main field. So we excite modes, we inject turbulence by exciting modes in a spherical shell in large scales. So it produces motions in large scales here, and it produces a cascade that you see energy in different scales of the system. The problem is that injecting modes very close to wave number parallel to magnetic field 0, it means you are putting what's not really waves. These modes are not bending the field lines, and they are there just because the numerical domain is finite size. So these modes, they are not properly waves, propagating waves. They mix the field lines without suffering any resistance. This is artificial. So we tested avoiding to exciting these modes, and we got some interesting results here, because when we use the usual injection of the turbulence, so this shows the diffusivity as a function of the parameters of the turbulence. So this line is what is predicted by the theory. Each point is one simulation, and this set of black dots are when you inject these 2D modes I told you. So in this case, we got a total deviation from the theory. This is what was happening with early simulations and from other groups too. This is because the 2D modes are mixing the field lines very easily without suffering any resistance. When we remove the injection of these artificial modes, we have something much closer to the numerical, to the theoretical prediction, like this green line. So to illustrate the effects of the size of the domain, so it was a criterion discovered by 2007 by Mazarenko. And he discovered that if you do not have a domain large enough compared to the size of the turbulence, you have some problems in representing the wave-wave interactions in this domain. So it leads to a deviation, total deviations to the regime of turbulence that would be expected in your simulation to represent reality. So we show here these different sets of simulations, domains, scenarios of different domain sizes. So 48 times the scale of the turbulence and 3 times the scale of the turbulence. So when we obey this criterion, we get closer to what's predicted by the theory, but when we use some common choice of the size of the domain, we get some deviation because of simply the turbulence is different from what it should be. So it compares here two simulations. They are exactly the same, except by the size of the domain in the direction of the magnetic flux, the regular magnetic flux in the domain. So we see here in this power spectrum how different is the development of the turbulence in both cases. So in the large scale domain, we found some convergence when we increase for a size large enough. So we represent something that should be expected. And when the domain is short, no. And by the last, the compressibility, we also found that when you take into account the presence of compressible modes, not only alpha-van waves and compressible alpha-van waves, in fact, you get some different statistics of the turbulence, and the rate of transport of magnetic fields is larger. I mean, it's less suppressed by the presence of a strong magnetic field. So the green line is the most compressible simulations we had, and the blue line is the most incompressible simulation. I mean, closer to the theoretical scenario. So it's not a surprise that it gets closer to the theoretical prediction, this blue line. So this is the theoretical prediction. And I will finish here. I'll just quickly read the key points of these presentations. Some star-forming process seems to require the violation of the frozen condition. The reconnection diffusion mechanism appears as a natural solution, and the comparison of its efficiency with other mechanisms depends on the quantitative knowledge of the reconnection diffusion rates. Or numerical simulation seems to be consistent with the theory for the diffusivity when approaching the incompressible limit, and showed an increased efficiency when turbulence is compressible. And this is a real result. In this star-forming environments, turbulence should be very compressible. And now the artifacts. The common choice of turbulence forcing in numerical studies introduce artificial effects that cause the diffusion coefficients to other effects, but also the deviation from the diffusion coefficient from what it should be. That's it. Thank you for your attention. Open to answer if someone has some question.
So thank you very much, Reinaldo, for this talk. It's very nice to see a subject that you started working 10 years ago, and you presented this in one of these challenges workshops with Opher. Very nice to see the conclusion or the developments. So for those of you that arrived late, something Elizabeth Dalpino was supposed to be the chair, but something happened probably in Belgium, and I'm replacing her. So we are coming to the end of this week, very busy week of talks, and I don't see anyone more appropriate to give the final talk for this workshop than Merav Opher. So Merav, can you share your screen?
Sim, deixa eu pensar. Thank you so much, Rogério. I cannot be more excited. Okay, great. I am sharing. Okay.
Yes, you're sharing, but not your presentation.
Now can you see?
Yes. So Merav, I tell you when you have, so it's 25 minutes, so I'll warn you at 20 minutes, okay?
Okay, great. Okay, Rogerio, and I cannot be more delighted to be here. Okay, so I don't have a whole lot of time to cover all this very broad subject of heliosphere, and so I'm going just to touch in some aspects that we're looking into. And before I start, I just wanted, again, because this is related to my dad, and here I put Brazilian Z, not an S, bad Merav. Anyway, to show the observatory in Atibaia, and me and my twin, Michal, and my dad, of course. So this is in homage of him, this talk. So anyway, so the heliosphere, the topic I'm going to cover, is related with this cocoon, this bubble that in fact, almost every star we think in the universe have. When you look up and you see the stars, you don't see very often these bubbles, these astrospheres, we call them, because they're very rarefied. It's not very dense, so it's hard to see. We do have some images, those are astronomical images of much more massive stars than the sun that have massive cocoons, you can see here, and they come in all sorts of shapes and flavors. I started this work many years ago, more than 20 years, and I'm going to tell you a little bit the trajectory and what we know now and what we are interested in discovering. One thing we know, and Adriana talked about it earlier today, is this chase of trying to find an Earth-like planet and the exoplanet work, and she talked a lot about the flares and the CMEs that can affect the atmospheres of planets. Another aspect that is often overlooked is the effect of the bubble, of the astrosphere that engulf the planets that we're looking. And we know from our own solar system that the bubble that it's, for our case, is called heliosphere. And just to give an idea, the size of this bubble is around 150 AU. So it's way beyond the planet, the size of it. When Voyager spacecraft that left this bubble in since 2005 and 2012, they are now in the interstellar medium beyond our heliosphere. They measure galactic cosmic rays. For people that do space physics, the energy that we're talking is 1 GeV and below. So those are for astronomers, low energy galactic cosmic rays. But those are very important for several effects related to origin of life. And we're still investigating the link of the presence of this galactic cosmic rays and habitability. But we know already from Voyager that the bubble around this planet shield 75% of this galactic cosmic rays. This is a graph showing the intensity of the GCRs when Voyager was inside the solar system, was launched in '77. And when it's left the solar system around here, you can see the intensity jump. So this slide was just to show the importance of studying the heliosphere, including relating to habitable aspects of exoplanet work. Another interesting aspect that I just want to point out before I go on is that the last layers of this bubble, what we call the heliosheath, where the solar wind is slow, it's actually subsonic. And those are the regions that mostly shield the galactic cosmic rays. So understanding that last layers, it's almost a 20 AU of thickness, is critical. And the last thing about this slide, that we have several indirect indication that in fact the nearby stars around us all have astrospheres. So it's not just our imagination, but we do the solar-like stars. And it's not just massive stars, we see solar-like stars having astrospheres. One thing to remember that the heliosphere is the only one that we can send probes like Voyager and study in situ data. And there is nothing like in situ data to kind of put to shame all your beautiful theories, and you have to throw them all out of the window and rethink about them. So we are using, in my work and others, the heliosphere as a benchmark to study other astrospheres like the ones I'm showing the background as a case of a known habitable astrosphere. I have a center, I'm still the PI of this center called SHIELD, and SHIELD come from this idea that we are shielding the galactic cosmic rays. It's also an acronym that I cannot, don't ask me to reproduce. It's something about solar, helio, whatever. But SHIELD, this is a center funded by NASA in 2 stages. We are now in phase 1. We are ending phase 1. We are hoping to get phase 2 with much more money for another 5 years to study this case of habitable astrosphere. I'm the PI, and John Richardson, that is a long-term member of Voyager, is a program manager. And we have a whole slew of people trying to study this, from co-Is to collaborators, some you might recognize. And we are trying to study some of the phenomena that even the last speaker touched about reconnection, turbulence, and all these basic physics processes, how they affect global structures as a heliosphere. Just to give you a flavor, I won't go to all these questions here. I want to focus in one particular to go a little bit more in depth, but the main questions this center, and not just the center, but the community is trying to address is, to begin with, let me start with actually question 4. We don't even know the shape of our heliosphere. And this is a question I want to dive into more detail. We also don't understand how far the heliosphere influence the medium beyond the heliosphere. Now that the 2 spacecraft Voyagers left the heliosphere, we do see an interstellar medium highly perturbed by the sun and the heliosphere. And it's not as we predicted, and it's hard to describe even the level of turbulence and the level of shocks and anisotropies that we see. So this is an area that needs further study. The main drive of this center is to try to predict this filtration of the cosmic rays, not just in one single point as Voyager was, but everywhere in this 3D structure. But the other piece, the physical piece of it, the solar wind is not a uniform distribution. You cannot even describe with a beautiful Maxwellian. It has longer tail. It's a very anisotropic distribution. And part of this very energetic particles in the tail are called pickup ions. And pickup ions are generated by the neutral hydrogen that come from the galaxy and penetrate into the heliosphere, get ionized near the sun, and become part of the solar wind. We don't understand this distribution that is not thermal, how it's evolved through the solar wind, and how it's get modified by shocks like the big gigantic shock that slow down the solar wind, to other processes like reconnection and turbulence. So this is a very daunting problem, and this is why we advocated for NASA to fund us for a center. And like I described here, we have all this research thrust in the center, and we're trying to build a predictive model. And of course, all these pieces and many talks that were described in this conference are interconnected, like a puzzle pieces. The part of the solar wind that is cold, that you could describe as a Maxwellian, interact with accelerated particles that we call here pickup ions. It's interact by turbulence, by wave particle, by reconnection. It's also interact with neutrons that come from the galaxy. not by Coulomb collisions, because it's very rarefied by another process called charge exchange, but it also interacts with cosmic rays. So the daunting piece of it, that you cannot just put like a recipe in a big global fluid model that are the global models. You need kinetic models like the last talk that describe the evolution of turbulence and reconnection. And you need to use your best theory and the best observation to benchmark this structure. So what I want to talk next is one topic that we are dealing, and to give you a flavor, some of the advances we made recently. Okay, so this is one of the major controversy that is raging in our community. That is, what is the shape of the heliosphere? And when I came to the field 20 more years ago, a couple of years ago, we thought we knew the shape. If you Google heliosphere, you will see that is the image that NASA put forward as the shape of the heliosphere. So the sun is in the middle. The sun has a wind that is supersonic. It has to slow down as it comes in contact with the galaxy. So it goes through a shock around 100 AU from the sun. AU for the non-astronomers is the distance us to the sun, Earth, sun. And it goes through a shock and becomes subsonic and needs to be deflected because it's in contact with another ionized wind. So two ion winds don't interact normally. And so you create this boundary between those two regions. And the idea that this tail will extend to many, many thousands of AUs. And this has been the paradigm since the 50s. We, in my group, put forward since 2015 this idea that the heliosphere is like a croissant-like shape. And this is the cover of Nature Astronomy 2 years ago that showed one of our simulations. One of the big piece of the controversy is that this is a model my group put forward, but there are other models that describe the heliosphere, one in Moscow and the other one in Huntsville, Alabama, and they get different shapes. And we would like to understand why different 3D models get different shapes, if it's numerical, if it's physical assumption, what is behind that? The other piece is that the observations of the heliosphere, and regardless, it's really tough to observe 3D structure, but you could do that through a type of tomography observations through energetic neutral atoms. If somebody asks me, I can go into more details how it's created, but you get shapes of the heliosphere, and in high energies, you get a spherical shape, while in low energies, you get type of lobes that were interpreted as a comet-like. So this is being controversial both in the observation side and both in the modeling side. And again, to put in perspective, Eugene Parker in the 60s explored this idea, not just him, but others, but he was one of the pioneers to think how the heliosphere would look like. And he explored two extremes. One, you have a star. This is at rest. And actually, you can put it in motion too. A star moving through the interstellar medium, but in the right-hand side, it's embedded within a very strong magnetic field in the interstellar medium. And the other one in zero interstellar magnetic field. And on the left side, you get the standard comet-like shape. And on the right-hand side, you get a tube-like that extend along the magnetic field direction. So this left-hand side become the paradigm because there were the first models that were developed to describe the heliosphere were developed in Russia by Vladimir Baranov group. And Baranov and Malama developed these models and were hydrodynamic models. And the solution that they obtained was a comet-like shape. So this became the paradigm. And if you study magnetosphere is also a shape like that. The magnetosphere of other planets are also similar. So this became like the view that people thought this is how the heliosphere would look like. I'm going to skip the observations for sake of time. But what happened in 2015, when we obtained this very different shape, we got back to some of the assumptions. One of the assumptions that people made so far was that the magnetic field from the sun was negligible. And the reason for that is that the plasma beta, the ratio between the thermal pressure and the magnetic pressure, it's much larger than 1 in the last regions of the heliosphere before it shocked against the galaxy. So the idea, if you have a very high beta, the thermal pressure is dominant, and you can kind of assume that the magnetic field is almost like a tracer, and where the wind goes down the tail, it just drags the magnetic field down the tail. Here is the equation for the standard Parker solution for the magnetic field from the sun. It's a radial field that includes rotation of the star. So you have a radial component that falls with 1 over r squared, and another toroidal component that falls with 1 over r. And this is due to the rotation of the sun, omega. And you can see that in really large distances, the field is like a spiral. This component is the only one that survives. So if you think about a spiral, like a circle, you are looking, let me go back, from along the rotation axis of the sun that is here. So you're looking from top to bottom, you will see a circle, right? And you can ask yourself how easy it will be for a wind that is trying to blow down the tail to drag this field line as a tracer. And so this is your magnetic field line, and you have the wind trying to go down the tail and stretching this field line. And in fact, when you calculate that, the thermal pressure doesn't play a role. What plays a role is a ram pressure, trying to stretch this field line, and the field line resists with the magnetic tension. So the force of tension has to do with the magnetic field intensity, the curvature of the field, and the stretching, it has to do with the flows trying to go down. What is interesting that, let me go back here. After the wind is supersonic here, but the wind goes to shock and becomes subsonic. And in this region here, we call it heliosheath, the ram pressure is small. And in fact, if you calculate the ratio of the ram pressure to the magnetic pressure, they're comparable. And in fact, the magnetic pressure is larger than the ram pressure. So you can convince yourself that if you try to stretch a field line, it will resist by the tension, and it will resist with this ratio. So if the magnetic field is strong, it won't be stretched anymore. It will try to maintain its circular shape. So we did some numerical simulations back in 2015. And here is the sun, the termination shock where the solar wind becomes subsonic. This is an interstellar magnetic field wrapping around the heliosphere. And the magnetic field of the sun that is shown here in white actually does not stretch and make a very long tail, but it becomes a tube that funnels the supersonic solar wind in a jet-like structure, one to the north and one to the south. And we actually revisited the idea of astrophysical jets. It's in a 2D model. This was led by my close collaborator, Jim Drake. And in this other analytic paper, where we explore the solution of an astrophysical jet in the regime where the ram pressure is comparable to the magnetic pressure. The thermal pressure doesn't play a role. So even in a very high beta, where the two little guys, the ram and the magnetic, are much smaller than the thermal pressure, the magnetic field is actually end up being the major player here in the heliosphere, collimating the solar wind and becoming the skeleton. So you can check the analytic solution and the numerical solution to convince yourself but this is being a major controversy in the community. Other models like the Huntsville show a similar, if you know this toy called Slinky, it's like, I don't know the name in Portuguese, but it has all these wires that can bend. You can see that in both the BU model and the Huntsville, the magnetic field behave like that. It doesn't stretch to large distances. Both models agree that you have this structure, and you can see what happened at the end of these jets. They're very turbulent. So there has been this suggestion back in 2015, both by my work and by this other work, that maybe these instabilities are driven by the standard instabilities that you know in jets, like sausage or kink instabilities.
Merav, you have 5 minutes.
Okay, cool. So what we did in the work that was just published this year, and this was in homage of my dad, so I'm glad to talk about it. I will skip this piece, was to investigate what is instabilities that drive that. So I only have 5 minutes, so I'm just going to give you a flavor, and you can check the publication to know more about it. But in fact, we show that when you turned off the neutrals that stream from the galaxy, the jets that are shown here, the cross section in a meridional plane, are stable. The instability only appear, this is when you don't have a motion through the interstellar medium, you have the sun in the middle and the two jets, one to the north, one to the south, and they're stable. But when you turn on the neutrals, and I'm going to stop, the axis of the jets start bending to the right because you have a charge exchange and you create a wind that bends the structure. But you also create, and I'm going to skip this movie to show that the axis of the jets bend. This is not an instability, this is just a wind that is created by the interaction of the neutrals with the ions that bend the whole structure. But you start creating those big indentation here that are Rayleigh-Taylor-like. And if you remember Rayleigh-Taylor, it's a heavy fluid sitting on top of a light fluid. If you have a gravity pointing from the heavy to the light fluid, you will make this whole situation unstable unless you have a magnetic field to stabilize it. And this has been discovered for the heliopause, the interface that separates the heliosphere from the interstellar medium, as existent because the neutrals interact with the ions with an effective gravity, a drag. But this instability can be stabilized in the interface with a strong interstellar magnetic field. What happened in the axis of our jets? The axis of the jets has no magnetic field because the radial field is very small at these large distances. But if you go back to the profile here, you can see that the density of the jet, just given by the tension force, has some gradient. It's denser in the center and lighter on the side. So it's a perfect situation for at least the right-hand side to be unstable. And there is no magnetic field to stabilize it. So we derived the Rayleigh-Taylor-like growth rate for this instability. It's a new regime for this instability. And we compared with several simulations the growth rate. So we measured how much the axis is going away from where it was going to go anyway if it was just bended. And we run several simulations with several hydrogen density from the galaxy, and the instability is very strong as you increase the hydrogen density and goes away when it goes to 0. And I'm almost done, Rogerio. And you plot the growth rate, and the models give you the dashed blue line, the theory give you the red line, and considering all the approximations we're making, that is a slab, beautiful slab, what is really not, we get a really good agreement. So in a real case, this is a punchline. This instability this is a case when we are moving through the galaxy. This instability starts as a hydrogen stream, It's make the heliosheets extremely turbulent, and the heliosphere that at first have a long comet shape like becomes split. So that turbulence in the heliosphere end up driving reconnection that let the interstellar medium comes in between the two lobes and creates this shape. So we are very excited about it. You can see in my paper why kink is not happening. It's actually stabilized by shear flows. But the main conclusion of this paper is that we think these instabilities that happen due to the fact that the heliosphere is embedded in a partially ionized medium drive the shape of croissant-like. So this last paper was dedicated to, was not lazy, last paper was dedicated to my dad, and I wrote is dedicated to Reuven Opher, who loved science deeply and fearlessly. Thank you so much for giving me the opportunity to talk to you about this work.
Thank you very much, Merav. I think slinky in Portuguese is something like mola maluca or something like
mola
that.
Mola maluca, tá bom.
Yeah, I used to have that.
Isso, eu não consigo lembrar o nome. Okay, mola maluca, okay.
And also I found the acronym for SHIELD. So SHIELD means, what is it? Strategic Hazard Intervention, Espionage, Logistic Direction.
No, that is not.
It's a joke, it's a joke.
Oh, because there's another one. There is a different shield.
I know, this is from Marvel Comics.
Rogério, tá aqui. Shield,
okay.
If you go Shield Drive Center, let's see. I think the acronym, where the hell is the acronym?
It was just a joke, Merav.
I have, yeah, good.
I can't resist making jokes, I'm sorry. But also, I want to remind people that we had a very nice memorial symposium in honor of Reuven Opher in January of this year. So it's all recorded, you can go there, and it's amazing. I mean, the life of Opher is truly amazing. So I really recommend, if you haven't seen the videos, go there, and we got people from the Haifa time, IAG time, or any time. So, and also from later time. So it was really an amazing event. It's all recorded, and just go on the webpage of ICTP-SAIFR and look for events in January, you'll see. So thank you very much, Merav, and thank you for all the speakers. I think we'll go directly to what we call traditionally the Paredão session, where we ask all the speakers to be ready to receive questions. So Gustavo, Adriana, Jorge, Greg, Reinaldo, and Merav, the floor is open for questions, people to shoot questions at you. So I see Marcos Maia. So if you have questions, just raise your hand and I call up, okay? Marcos Maia.
Okay, thank you. Merav, thank you very much for this very nice exposition. And I was wondering here, if you have foreseen any way to simulate those cocoons in a laboratory.
You mean in astrospheres?
Yeah, in the Earth. I mean, just...
Yeah, this is a very interesting question, Marcos. I think we can. I haven't looked much more into it, but there is a group in Portugal that has done mini magnetospheres in laboratory with lasers. It's a laser group back in Portugal. I don't know, that will be, it's a very interesting question. And I can imagine that one can design scale down version or comparable, at least capturing the main physical processes and explore. That is a very good question. I don't know, Marcos.
I'm thinking about a tokamak. That would be a good shielding for a tokamak, wouldn't it?
Right. Yeah, you need to just think about the geometry of the magnetic field, that you have this effect of you have a wind trying to blow the magnetic field, or unless you say, okay, now I'm in the regime that I'm in the jet. and the magnetic field confined it. And now you can study the turbulence, because this is the other topic I didn't go into, but this instability will accelerate particles. And I'm very interested to explore, maybe I can start collaborations here with several groups on what are the best tools to explore this turbulence driven by this instability, how it accelerates particles. I am not sure what the best venue, how to go about it. But experimentally is super interesting.
Thank you very much. Very nice. Thank you.
Okay. So while people are thinking, I have a question for Adriana. So Adriana, I was really fascinated by your talk. It was amazing. So do you think this is an explanation why life on Earth started underwater, just to protect life from the ultraviolet radiation from the sun in those conditions?
I mean, of course, I don't know. I don't think anyone can answer that. But one thing is true is that with the arcane atmospheres that Earth had at the time, when when Earth and the Sun were about 2 billion years old, any ultraviolet radiation from such strong flares like that super flare that happened on Kepler 96, which is very, I mean, it's a twin-like star, solar star. All the DNA would be just completely damaged. It wouldn't survive. It would sterilize the surface of Earth. But of course, like under rocks, maybe Mars, if they're at the same time, maybe something under the rocks, or definitely, and it's just like 30 meters of water would be enough. So lakes are fine. It doesn't have to be deep ocean. So that's what we found for TRAPPIST-1 and especially for Earth.
That's amazing. It's really amazing. Okay. More questions?
Can I add something there?
Yeah, of course.
The events from catastrophes like gamma ray bursts, close supernovae, and so on are much more harmful than the regular flares from stars, even the super flare, the very high level ones. Therefore, what really matters to my mind is to try to preserve the base of the chain food, which is the plankton itself. So the plankton, by the same reason, they need to be, in shallow waters to absorb the light. Is very heavily affected. Therefore, we had some calculations about flashes and the thing. People say, okay, it's just one hemisphere that gets illuminated and that's it. But these are global effects. So I believe that Adriana's calculations also show that once you strike the biosphere, and that you cannot restrict yourself the damage to have an hemisphere. And by the way, most of the geological history will have to deal with marine creatures, not with the Earth. Even though we always think about sterilizing the Earth and so bacteria and so, but those are modern organisms. Therefore, what really happens is tied to the very ancient atmosphere, not necessarily the modern one, which has the buildup of the oxygen, the big oxygenation and so on. So there are many concerns there. One of course, these kind of flares from stars are very common. So it's a matter of taking care of all the details and also to wonder whether the mutagenesis is affected too, because it can be an evolutionary driving force, not only distracting the organisms, but rather to prompt a rapid evolution. So there are many things over there that had to be gauged properly. So we started to learn here and there what happens, but it's still long way to go.
It's still fascinating. Well, just the fact that the water, most of the water, as far as I know, comes from meteors, right, on Earth. So there was a phase where the Earth was heavily bombarded by meteors that brought the water, and then the oceans formed, and then life. So is this the right sequence? I think it is.
Yeah, that's it. What I mean is that most of the geological history of the planet will have to deal with organisms that live in the water, by the way. And therefore, you should first concern about what happens with the phytoplankton. And well, phytoplankton, the present phytoplankton is a modern organism as well. So it's not very easy to match those ancient forms of marine life and to gauge what the effect is, because, for example, her calculations use modern organisms, as they should, but they are modern bacteria. Therefore, we really don't know whether we have to resort to some archaea or something else to be closer to the real situation. And
Okay.
giga-year or 2 giga-years ago, something.
Adriana, you want to complement?
No, that's it. Well, okay.
Yeah, I mean, no, yes, I mean, I agree with Jorge, but Katja, why is your name Katja? But well,
It's a long story.
okay, sorry about that. But yeah, I mean, yes, I mean, we did use Escherichia coli is definitely
You should, yeah.
modern bacteria. Deinococcus radiodurans is an extremophile, but I don't know if it's an archaea. I don't think it's an archaea. And
I tell you this because I've been criticized by the referees who say, oh, you cannot put a bacteria living in the guts of people as an example. I say, but this is an extremophile. And therefore, there are some other radiococcus, the radiodurans is another. There's another one that was isolated in Atacama by Douglas and company, which is extremely resistant. So fortunately, it's not pathogenic, because otherwise we will be completely, erased from the. Not only the COVID is against that, but there are many other things there. And there's little evidence for an increase of mutagenetic rates along, for example, the big extinctions, which is surprising. Because you may wonder that if something strikes the biosphere, then the mutations will have to take over to refill the ecological niches. But this is not what happens. Therefore, these ideas that there were, catastrophic events striking the DNA is not really supported, not fully, at least by the scarce evidence we still have. So there are many things to worry about. But you're right. I find it extremely fascinating, this ongoing interface between astronomy and biology and oceanography and so on, and geology.
So I have another question for Adriana. Sorry, Adriana, go ahead.
No, I was just going to say that I also gave this talk at Astrobio from National Observatory, and I was. There was a comment about that's how it's called, stromatolitus. I'm sorry, I don't know how to say that in English, because they are like mineral-like structures, and so those might protect the life forms, that live inside them. I think they're made out of calcium or something like that from your ultraviolet radiation, but.
Well, stromatolites are a really interesting case, because they're very old. They're 3-point-something giga-years ago, and they are photosynthetic. So they hold colonies of some people call them primary corals, because they were 3 billion years ago they were there, and essentially are the same stuff. So they are not related with modern corals, but anyway. And there is a protection from the very structure of the calcium that holds the colonies. But as far as I know, there's no clear-cut evidence that they could or could not have survived, for example, an example like that. Even though they live in shallow waters at around 1 meter or so, because they need the water. That's what I meant. That the same thing that feeds the animals is against them, because if they do not know that the UV is going to increase like that. So it's very, very funny.
Yeah. So the other question is about the variation in the brightness of our sun. So it's 0.1%, you said, these days. But it was
Yes,
much
that's
larger.
what.
It was much larger in the past.
Well, if we assume that it behaved like other stars, yes. I mean, we have some very young stars which have like brightness variations of the order of 6% of the total brightness.
So the question is,
And not only that, but like the 6% is not even from the cycle; it's from rotation.
wow.
That's from rotation.
So it's 6% in a very short period of time.
Yes, in a few days. Yeah, it goes up and down. Yeah.
So that also can affect life, I suppose, right? 6%. I'm not sure.
Yeah. Well,
enough to affect life. Anyways,
yeah, I haven't done the calculation, but I believe so, because I mean that's with all this climate change, right? People are trying to estimate what are the contributions from the sun, and of course variations of this. I mean, the sun, the solar flux has been increased by about, it was 70% dimmer or in the past, right after it formed. So it is an increasing process, you know, like due to stellar evolution. So that's something else. What is it going to do, you know, like to help, you know, like to contribute it to man-made, you know, like global heating, man-induced global heating.
By the way, let me add, which is a curious thing, that the first thing I faced as a student, as a research problem, was my advisor's one, which devoted some time to record the increase in the luminosity of the sun by the stromatolites. And there were a huge variation, because his idea, well, his general idea is that the cosmic events are recorded in atomic times, which means the growth of the structures, and therefore you can see the duration of the day, the illumination, which is the luminosity of the sun, and so on. And those are pretty much very well understood records in paleontology, and support increases of the order of 70% for the early sun luminosity. Okay, which is amazing, because it's a completely independent way of, you do not talk about HR diagrams, other stars, or whatever. We simply have the record in the fossil stromatolites and many other things.
Interesting.
Any other questions, people? Come on. I have a question for Merav. It's very naive. So Merav, when people were planning the trajectory of the Voyager, do they plan it to go in the direction where the heliosphere is shortest? They knew that?
No, they didn't know. And actually, in fact,
so
now
was sheer luck then.
Was sheer luck. But no, was what happened is, it still is a case that the main way to get out of the solar system is by gravitational assist of the outer planets. And both Jupiter, Saturn, Uranus were aligned in a way that you can get the gravitational force to let them go. And there was an engineer in JPL that noticed that they were aligned. So it was the time, this is why they raced in 77 in September to let the Voyager escape.
So it could be wrong, right? It could go the other side, and then it will never.
Could have been, but the interesting thing, now we are trying to plan the next probe after Voyager, interstellar probe, and it's not necessarily the case that the nose is more interesting. I am advocating to go much more towards the tail. The tail seems very interesting in terms of physics. The problem that you're going to leave the heliosphere if it's a shorter tail, like I think it is, but you're going to enter into the interstellar medium that is what we call mediated by the sun. So you're going to see turbulence generated by the sun, not the pristine turbulence.
Oh, that's that's an interesting piece of history that I didn't know. So it was kind of a coincidence that that you saw the end of the heliosphere. Okay, any other questions? People are very tired. So I don't see any hands up. So, so before closing, I want to thank Tiago Codinotto, who is invisible, but he's here with us all the time. And he's the person that arranges Zoom, records everything, put the videos on. So I really want to thank Tiago for all this work. And Jandira, you probably have received emails from Jandira, executive secretary of the ICTP-SAIFR. And they all deserve a big, big thanks to help to organize this event. So thank you for everybody for participating. And everything is recorded and we can go back and watch, etc. So I think it was a fun event, even though it was online. And
thank you for organizing, Rogério.
That's
Great.
okay. It actually was Marcos Maia who insisted that
Oh, Marcos Maia. Obrigada.